So in this video we want to explain what a linear transformation is and then explain why matrix transformations that we saw in the previous homework assignment are actually linear transformations. So the definition of a linear transformation says let U and V be arbitrary vectors in Rm, so some m-dimensional space, and let C be a scalar. So C is just some real number, right? When we say C is a scalar, we're just identifying it's an element of the real numbers. So a transformation T that takes elements or vectors from m-dimensional space and sends them to n-dimensional space is a linear transformation if these two criteria hold. So this first one says if we add the vectors first and then transform them, we need to get the same result as if we transform the vectors first before we add them and then add them together. So again, this is called addition preserving, and the idea is we want to get the same thing if we add first and then transform as we do if we transform the vectors first and then add the results. And then the second criteria that has to be met is that we want to multiply a vector in Rm by a scalar C and then transform it. And if we get the same result if we transform the vector first and then scale it, then we say scalar multiplication is preserved and we have met the two criteria that we need to be linear transformation. So these are the criteria that have to be met. And in subsequent video, when we prove that a transformation is linear, this is what we need to show. We need to show that these two criteria are met by the transformation. If a transformation doesn't meet these criteria, then it's not linear. Now in the previous homework, we looked at matrix transformations. We looked at transformations that were done by multiplying a transformation matrix by a vector and then sending it from Rm to Rn via this transformation matrix. And it turns out that matrix transformations are always linear transformations, and this result just comes straight from the properties of matrix multiplication and addition that we looked at earlier in the semester. So if you were going to prove it formula, you would say, if you were going to prove this formally, what you would do is identify a matrix transformation and say, hey, let T be a matrix transformation that maps from, I should have this from Rm to Rn so that I'm consistent with what I have up here, and let U and V be two elements of Rm, and let C be a scalar. So we create the guys that we have up here, vectors in Rm and a scalar. And then what happens if you add the vectors first, because that's what this says. It says add them first and then transform them. So add the two vectors first and then transform them. But transforming them, if it's a matrix transformation, it's just a matter of multiplying by the transformation matrix A. So we do transformation matrix A times the sum of the vectors. But we saw that there's a distributive property when we're working with matrices. So this matrix will distribute into U and V, which we did here. There's the distribution. But if we multiply the transformation matrix A times the vector U, that's the same as transforming U, plus, bring the plus down, if we take the transformation matrix A and multiply it by V, that's the same as transforming V. So we've met the first criteria that needs to be met for a transformation to be linear. And then the second one would also just come straight from our matrix properties. So this says, hey, what if we scale the vector first, we want to get the same thing as if we scale the transformed vector. So here, scale the vector first and then transform it, but transforming the scaled vector is the same as multiplying the matrix A times the scaled vector, but this is just a matrix times a scalar times a vector is just is a matrix. And we've already seen earlier in the semester that the scalar can be factored out front. This is one of the properties we had for scalar multiplication. And if we can factor the scalar out front and multiply A times U first using the associative property, one of the associative properties, well, A times U is the same as the transformed U. So because matrix transformations meet the criteria to be a linear transformation, it turns out that every matrix transformation of the form A times a vector, transformation matrix A times a vector, is also a linear transformation.